Welcome to all of you to our webinar section. Today, where we are going to talk about the pharmaceutical preformulation and thermal analysis. So, I am Ligia. I'm a pharmacist by training, and I have a master's degree in biological science. Both of these degrees, the bachelor and the master degree, are from the Federal University of Minas Gerais in Brazil. I did the doctorate in pharmaceutical technology at Martin Luther University here in Germany, where I have also worked as a postdoctoral researcher on the development and characterization of drug delivery systems. Currently, I work as an application scientist at Niche Analyzing Testing. I work specifically with the application of thermal analysis and rheology in the fields of pharma, cosmetic, and food. So I think that we can now start with the topic. I will turn my camera off, then you can just focus on our slides. If you don't have time at the end to answer the questions, you can feel free, you can write them during the webinar presentation, but you can also address these questions to me afterwards by email, using my email that you give at the end of the presentation. But I will return to all of you, and I will be glad to give more information or to clarify the doubts that we have regarding the thermal analysis and rheology. We're not talking about rheology today, but yeah, I will be glad to answer all the questions that you may have at the end. So let's start. Our agenda for today is the definition or the more explanation about the preformulation itself and the thermal analysis methods. Specifically here, we are going to talk about differential scanning calorimetry and thermogravimetric analysis. And I will give application examples on the field of preformulation. The first is how to develop a drug candidate into a drug product, which is the way that we do that. The first answer that can come to our minds is by design a dosage form, the dosage form design, or via the formulation stage. But what determines the final design of a dosage form? Considering that the aim of a dosage form is to achieve predictable therapeutic response, it has to have at the end the reproducible product quality, and the result should be independent from patient to patient variation, which is something quite difficult to achieve. A drug may be formulated in different dosage forms as tablets, capsules, syrups, solutions or suspensions, creams, paste, ointments, and injections, intravenous, intramuscular, and implants, solid implants, macroparticles implants, so many other types. The point is that the dosage forms may have various strengths, and each being suitable for a specific application or a group of patients like pediatric or elderly people. But always the bioavailability of a drug has to be considered. That is the main concern. How much of a drug will achieve the therapeutic target? So the bioavailability of a drug must be always in our mind. But to get to this formulation process, this formulation stage, we need to know the drug itself, what happens with the drug, which are the characteristics of such a drug. A drug candidate does not burn alone. Usually, a set of chemical entities have a defined pharmacological target is developed by the chemists. In fact, the development of a new drug product starts with a dozen or more of drug candidates, and only a few of them, if much, will become a pharmaceutical product. And for that, the physical-chemical properties of each drug candidate has to be investigated. How about their stability, interactions with excipients, and again, bioavailability? Um, these properties can be split in two different categories, the molecular and the macroscopic properties. The preformulation is the step on the drug product development where the physical-chemical properties of a new chemical entity are determined. And we see here that the different molecular properties, solubility, pKa, partition, log P, hygroscopicity, and stability. And TGA and DVS are the methods for determining the hygroscopicity of a sample. These essays here are presented in the chronological time, the chronological order that has to be determined, as suggested in the Alton's Pharmaceutics book. About the macroscopic properties, the melting point, enthalpy of fusion, and physical forms that are completely related to each other can be defined and characterized by DSC. But we also have to define particle shape, size distribution, rugosity, and habit of these shapes. Density is also important to be defined. Flow and compressibility are a function of particle shape and size distribution, but must also be determined. And I step further in the direction of the formulation stage itself is the excipient compatibility, but it can be defined here in the preformulation. And the excipient compatibility is determined, characterized using DSC or HPLC. So we see that here the thermal analysis present in many of the steps of characterization, but we can also use information related to DSC that we get from the DSC studies to calculate, to estimate the ideal solubility. And the thermal and oxidative stability can be determined using TGA. And also purity, salt, and polymorph screening and plasticizing effect can also be determined in this step using the thermal analysis tools. How about the thermal analysis? One of the methods that I'm going to show to you is the thermogravimetric or thermogravimetric analysis or thermogravimetry. And I can say that a thermal balance measures the mass change of a sample as a function of temperature or time under defined and controlled environment with respect to heating rate, gas atmosphere, flow rate, crucible types, and any other parameter that can influence the measuring. Thermal stability, the composition, water content, amount of solvents, can be determined using TGA. And we can also analyze which kind of gases are evolved from the furnace when we have coupled to the thermobalance FTIR spectrometer or mass spectrometer, for example. And here On the left-hand side, we see a principle of a top loading thermal balance. So the furnace is not directly over the balance. We have the furnace, here the sample carrier, and the thermocouple that will measure the temperature here. Okay, then we do have the differential scanning calorimetry. A differential scanning calorimeter determines the difference between the rate of the heat flow into a sample pan and that into a reference pan as a function of temperature or time. During such a measurement, the sample and the reference are subject to the same control temperature program and specific atmosphere. Before we measure any sample, we have to do a temperature calibration and a sensitivity calibration of the device. It must always be performed before the measurement. And all these aspects here in the left-hand side must be considered. The crucible type, if it's from aluminum, for example, if it's open, if it's closed, or if we have a pierced, it's closed but with a pierced lid. The temperature program here, an example of a temperature program of from 25 degrees C until 600 degrees C, with a heating rate of 10 Kelvin per minute. So this is the temperature program. And which gas do we have, at which flow rate we do have it. And it's important to keep in mind that when we are comparing samples, the masses must be similar. So this is something that is also important. It's not important for the calibration, obviously, but this is important for the comparison of the results. And melting and crystallization behave on glass transitions, polymorphism, and compatibility are some of the applications that we do have. We can use DSC to characterize in pharmaceutical field. About the molecular properties, the first example here is the hygroscopicity, and it's measured using TGA. The sample is the alpha lactose monohydrate, which is mainly used as a filler for tableting. And the affinity of the lactose products to humid air depends on their modification. Pure lactose monohydrate products are very stable to humid air. In contrast, when we have amorphous lactose, it is very hygroscopic. At a certain humidity, amorphous lactose is transformed into crystalline alpha-lactose monohydrate form that exhibits change in its compression properties. This sample here contains about 10% of amorphous lactose. Using TGA, we can determine the water content of the material. We can also determine how these materials behave in the presence of humidity, as we can see later. And here the green curve shows the lactose as received. The first step here, 0.5% of mass loss in the range of 100 degrees C, can be attributed to adsorbed water. This parameter is called loss on drying, and for alpha lactose monohydrate has to be smaller than 1%, accordingly with the USP. The second step here is due to the release of the crystal water, which corresponds to 5% of the mass of the molecule. So it's in the range. The water content for the alpha lactose monohydrate, accordingly with the European Pharmacopoeia, has to be between 4.5 and 5.5. So here we are at the range. And the thermal degradation starts here at its onset here, has its onset here at 224 degrees C. In this example, we can also evaluate the influence of moisture on the material. The sample was stored in an open container that was placed inside a vessel filled with water. There was no direct contact between the substance and the water, but it was here inside here of this content for this vessel for 2 weeks. And here in blue, we see what happened with the sample. The humidity storage yields an increase in absorbed water from 0.5 to 4.5% in the blue curve. But there is no influence on the amount or the other steps, the further steps of the curve. So we have here a second step that it's probably related to the crystal water, the release of the crystal water. And then here we do have the decomposition at 200 to 24. And we see here the TG and the TG, which is the derivative from the TG signal. Another example regarding the hygroscopicity or is the absorption analysis. This is one method to the dynamic vapor absorption is one method to determine the influence of humidity on a substance behavior. This DVS, this dynamic vapor absorption, has the changes in the sample mass in the presence of different vapor amounts, or the relative, in this case here, of the water vapor. And we see here in the blue, by the blue curve, the change on the relative humidity, and here in green is the TG curve. The results demonstrates that a strong hygroscopic nature of the microcrystalline cellulose, the first increase in the relative humidity from 0 to 20%, here in blue, induces a mass increase of 4%. So it comes from 100 to 104 here in the TG curve. The subsequent steps show that the higher the relative humidity, the higher the mass gain, until 80% of relative humidity, where we have a gain of 12%. As soon as the humidity level decreases, the absorbed and adsorbed water is released, resulting in a mass loss and coming back at the end to the 100%. So all the water that was absorbed was then released. In the right side is the hysteresis is highlighted. This hysteresis process is highlighted. The moisture content is higher during the desorption when compared with the sorption. So the final and the initial and final points the same, 112, obviously. So we come back to 100, but the way or the speed that the water is adsorbed and then desorbed is different. This is called hysteresis, and it's typical for porous materials. So let's talk about stability then. The main method to define stable hydrolysis, photolysis, oxidation is HPLC. But we can do that. We can also determine that using the TGA. And we go back to the alpha lactose monohydrate. And we see again this green curve. This sample was analyzed with thermobalance coupled with infrared FTIR spectrometer from Bruker. The figure depicts the mass loss curve here in green, as we have seen before, but also the derivative, the first derivative of this curve. We also see here in black this Gram-Schmidt curve. The Gram-Schmidt curve indicates the amount of the evolved substance detected by the FTIR during the heating process. So we see that we have something here at 144 and something at 303 degrees C. But with the help, with the gas analyzer, with the FTIR, we will collect the spectrum of the material that was evolved, and the software creates this 3D cube with all the spectrums. We can decide to find the temperature of interest. Here I'm highlighting the first step here, that is related to the release of the crystal water, and 2 steps in the degradation process. We can decide here and at which temperature we are going to take to extract 2D spectrum, and then we can analyze this spectrum, comparing it with the library. The software has a library and that comes with the software, but we can also create our own library. So in this case here, I'm showing you 2 different spectra, one here at 150 approximately, and another at 238, 140. And both spectra are similar, and they agree with the water spectrum from the library. It seems that here is as stated before, as suggested before or said, that we do have the crystal water released, but here the first step of the degradation is the release of water. If you go further here and check what happens after this peak here in the DTG or after this peak here in the Gram-Schmidt curve, we can compare the acquired spectra with our library, and we do have the degradation. It's clear that we do have degradation because this spectrum here is compared with 2 different. We have probably the involvement of 1,2-ethanediol and also CO2. So it seems that using the FTIR spectroscopy gives us such an important view and can give some insights about the process, the chemical reactions that happens when we do have a TG curve. So it brings more information for our analysis. For about oxidative stability, diclofenac sodium was submitted to the TG under 2 different environments. The first line here in blue is the TG curve of diclofenac in air, and the second here in green is the line of the diclofenac measured in nitrogen, in inert atmosphere. And again, we can check. So it's clear that we have 2 different processes. One in air is the combustion of the material, and in nitrogen is pyrolysis. And the oxygen has such a big influence of the presence of oxygen has such a big influence on the products, on the way this chemical reaction happens. In the same way, we can evaluate what happens in each curve, extracting to the spectrum from the temperature that we have interest on. And here I took these 3 examples here, and we see when checking the CO2 here as an example, we see that at 300 degrees C, we have such an amount of released CO2. This amount increases over time, but at 350 degrees C, there is no CO2 anymore. This is in air. When we analyze the spectra from this sample evaluated under nitrogen atmosphere and an inert atmosphere and checking again the CO2, we see that it will just appear later at 340 degrees C. So we can say that we do have two big difference. We have big difference on the reaction that happens in different atmosphere. So with TGA, we can check the oxidative stability when we do have oxygen on when we have air, and also the thermal stability when we just have an inert atmosphere. The evolved gas analysis is an extremely useful tool in the thermal and oxidative stability, but not only for that, we can use and apply it easily to define and understand what's happening inside the thermal balance. Let's go to the microscopic properties. And here this example is the risperidone. I have here on the left-hand side just a picture to remind us what means being a crystalline structure. The molecules are aligned to each other, and it forms a lattice, crystal lattice. It is close together, and it's hard to break this structure. And when we hit this structure, at a certain point, it starts to melt. This is a characteristic of a crystalline material. And we have here 3 important information: the peak, when the complete melting has done, the melting is finished, and the area under this curve, and the onset, the extrapolated onset. So this sample here was heated the first time, and then it was cooled down. And during the cooling, we see here in the range of 130 degrees C that we have a recrystallization. It's this exothermic effect here. When we heat it up again, we see again a crystallization, but in a different form. It can be different polymorphs, so the lattice can be rearranged in a different way, or it can be due to some impurity. It can be studied in depth to understand what's happening. But going further, what means this onset? This is the extrapolated onset, something it's here. And it is taken as the starting point of the melting. It can be clearly determined, and it's the method of the ISO and USP. For polymers, the melting range is characterized by the peak temperature, not by the onset. Another important information here is the enthalpy of fusion, which is given by the area. This is the integrated peak area converted from the millivolts seconds per milligram, which is the primary signal of the heat flux DSC. So this is the conversion from millivolts seconds per milligram to milliwatt seconds per milligram. Milliwatt seconds per milligram is the same as millijoule per milligram or joule per milligram. This conversion is calculated by the application of the temperature-dependent calibration factor K, as we told before that we have to calibrate the device. And the molar enthalpy of the fusion can be calculated just by multiplying the enthalpy of fusion by the molar mass of the substance. So these are 2 important information. Here just a short example of how it works related to the melting, the beginning of the melting, and how the structure of the material can interfere. We have the stearic acid that starts the melting at about this sample here, about 54 degrees C, has a peak here at 58. When it's cooled down, we see the recrystallization, and then melts again when we heat it up again. The point is that for pharmaceutical applications, we can find 3 different types of stearic acid. One with 50% of stearic acid, another with 70, and another with 95% of stearic acid. The other part of the other substance that is present there is the palmitic acid, which is a bit smaller than stearic acid. And you see here that the higher the amount of the stearic acid, the higher the purity of the stearic acid, the higher is the melting point. That's because the molecules can interact and create an orientation easier when they are more similar to each other. And in this case, obviously, we are talking about this 50 stearic acid 50 with the melting range of 54 until 56. Okay, melting temperature and enthalpy of fusion can be used to determine the ideal solubility. The ideal solubility is estimation of the capacity, the solubility of a material. And in a thermodynamic way, having some considerations, we can apply the Van Hoff equation to get this information. And so we have here the enthalpy of fusion and the melting temperature that we can apply. So this is an example from the Alton's Pharmaceutics, and it is about the ideal solubility of aspirin at 24 degrees C. I have here a measurement, a DSC curve from DSC that we have done here in-house, and we see that we have the onset at 137 degrees C, and this area here, we can, if you compare these values here, you see that they are quite similar. We have here just one detail, because we see that the baseline has changed a bit here. So the question is the material intact at the end of the melting? And we have to be really careful with that, because if the material is not stable, we can make only an estimation of this enthalpy of fusion. In this case, it's okay, the results are comparable, but we have to be really careful with that. And this, just to remind you that the enthalpy of fusion is the area under this curve, under the peak. So if you have some change, the enthalpy will change, but keep it in mind. Another application is to calculate the eutectic purity of a material using the same parameters. So for example, here you can see that we do have a flat baseline. So in this case, we can apply the Van Hoff plot and get, in this case here for this nipagine, it was 99.86 mole percent pure. So this is another application that we can have using melting temperature and enthalpy of fusion. And it's important to say that when we receive the material, the drug candidates, they are not totally pure. So sometimes it can be important to define the purity of it. So if we, in one hand, we do have this crystal lattice structure that gives the melting point, when we have amorphous material, we will not see this point. Instead of having a melting peak, we will have a glass transition temperature. That means that the glass transition temperature is connected to an increase in the specific heat capacity of the material. And that's why we see this step in the endothermal direction in the DSC curve here. The first heating brings the influence of the history of the material, how it was produced, how it was stored, handled over the months or maybe years, and was this material in contact with any material that could act as a plasticizer, something that can interact with these molecules here and change this glass transition. What glass transition means? Below this temperature here, we have a solid like a glassy material. Over this temperature, we have a more rubbery material. So at the first heating here, we do bring all the history of the material, then we cool it down. This cooling is made under certain conditions that it's controlled as we defined it before for the method, for the DSC method. And at the second heating, we can access a more reliable temperature range for the glass transition. So normally when we work with polymers, with amorphous materials, we take the second heating curve for analysis. And these curves here are of PLGA 52A. This is 50% lactic acid, 50% of glycolic acid with a specific molecular weight, and this is one of the most applied polymer for implants, the commercialized implants that we have nowadays. Here is just to show the influence of the composition of the material on the glass transition. Here over these two upper curves are from PLGA, LAGA 50/50, and the third and fourth curves are from lactic acid, polylactic acid, only one type of molecule. And this change in the molecular structure will give a shift on the glass transition temperature. And you see here again that we are just checking on the second heating of it. It seems that this number here is related to the molecular weight of the polymer, and it seems that it's not really important for in this specific case. Okay, we have sorry also an example of a semi-crystalline material. This is a PLA for injection, so it's for industrial applications, not for pharma applications, but it's an interesting example how it looks like. We have other applications, other examples in pharma, but this is such a clear example that it's nice to show. We have here the first step, the first endothermic effect here, which is a glass transition, characteristic of an amorphous material, and here we do have a melting range. And as I said before, for polymers, we have a range, and the peak is the important number. This is related to the broadside distribution of polymers. During the cooling, we see that we have no recrystallization, but then here the specific heat capacity came back to another level. And during the second heating, we just see the glass transition. So for a period of time, this material will be amorphous, but with time, the molecules will be rearranged once more, and then again we will have this semi-crystalline structure. So amorphous and crystalline regions are present in the bulk material. Talking about this lattices. I said that when we have amorphous material, the molecules are not arranged at all, and we have the crystal lattices. When this crystal lattice is in its and it's thermodynamic stable, when all these molecules are well aligned, then we will have the stable polymorph. On the other hand, we can have some arrangement, during the process of production or handling, we can have a rearrangement of these molecules, giving a metastable polymorph. The point is that with time, amorphous material tends to form the stable polymorph, or maybe it can come first to the metastable polymorph, but it will eventually goes back to stable polymorph. So this the arrangement of the molecules will give different properties of the solid. We can imagine that, for example, water solubility will be higher for a product that it's not in a lattice, orientated in a lattice, and it will also be different when we have this that's not so organized as here in the metastable polymorph. This is extremely important in pharmacy because the time that a metastable material goes to the stable polymorph can be days, can be hours, can be months or years. If we have the physical-chemical characteristics from metastable polymorphs that are more interesting for the formulation, we can use that. There is no problem. But we have to be sure that this change on the structure will take place after the shelf life of the product. If it happens before, we will change the bioavailability of our material, and it will change the therapeutic efficiency of it. And there are cases in the market that it happened. The material has the dosage form, the pharmaceutical product has to be withdrawn from the market because the bioavailability changed when the metastable polymorph became changed again to the stable polymorph. And the example that I'm going to show here is of the sorbitol. We see here from the literature that we can find sorbitol in 3 different crystalline forms, the anhydrous, gamma polymorph, and a metastable form. On our first heating here, we don't have here the onset, that extrapolated onset, but from the peak here, we can see, or we can assume that we are talking about the gamma polymorph, which melting point is at 98 degrees C. When it's cooled down and again heated, so the second heating shows us that we do have an amorphous. So during this process of heating and cooling, the lattice was broken, and it was then the sample didn't have time to rearrange the lattice, so we have amorphous material. But when this material is left at room temperature for 24 hours, we do have the reorganization of the molecules in a second, in a different lattice order, as we can see here by the temperature. So from here we have, at the beginning, we had only 1 peak, and here we have 2. And accordingly with the literature, this form that we do have in this condition here is called crystallized melt. Then the X-ray powder diffraction comes to help us in this point, because we can say that we don't have, or we can see, we can it's clear that we don't have the same material here. But how to prove that? We can use then the X-ray powder diffraction to prove. And here there is a standard, the reference of the sorbitol gamma, and in black here we do have the diffractogram of our material, and they agree quite well. So yes, as received, we do have the gamma form. But when we compare our material, that is the gamma form, with the third heating with this product that we obtained here, we see that we do have something completely different. So it's the same sorbitol, but the molecules are rearranged in different lattices. With time, it goes to the gamma form. If has no water, if has water, if has no water, it will be aligned in as the anhydrous polyform, and it will give a different DSC profile. So this is important, as I said before, because this change from the metastable to the stable polyform is very important and has such a big influence on bioavailability of the drugs that we are talking about. Regarding the physical forms, DSC and X-ray powder diffraction can be applied for two different things besides the basic characterization, for polymorph and salt screening. For polymorph, one of the tests that has to be done is taking this drug material and solubilize in different solvents, for example, at different speeds, changing the conditions that the crystals are formed, and then check if we do have polymorphs. It has to be tested. And this is called polymorph screening. Another point that we can use DSC is to salt screening. If we do have a drug that is poorly water soluble, but we can change its structure, forming a salt from it, and the salt formation will not change the pharmacological effect, and will increase the water solubility, then we can create salts. We have many examples of salts in the pharma industry. And DSC can also be used to screen, to do the screening of the formed salts during the drug candidates or during the definition or research of new possibilities for drug candidates. Okay. The next example here is related to the excipient compatibility. So we have some drug candidates after doing all these experiments. So it can be formulated as a pharmaceutical product, but is it compatible with the excipients that are used for formation or for the formulation of the dosage form? Then we can use DSC to check the compatibility. Here is a classic example, is the acetylsalicylic acid and magnesium stearate that are not compatible. And we see in blue the curve of the acetylsalicylic acid, and in red the magnesium stearate. Here in purple we have a physical mixture of magnesium stearate and acetylsalicylic acid, and we see there is no peak from the acetylsalicylic acid. So something happened, there is an interaction. We don't know which kind of interaction, we know what happens, but the point is we do not have two materials that are together without interaction. The software from Netch, the Proteus software, has a feature called superposition. This is a calculated curve from two different materials. We define, for example, here 1:1, the mass ratio from both material, and then the software gives us which would be a curve with no interaction between the materials. So you see here in black that in a normal way, we would have, if there is no, not in a normal way, of it, there was no interaction, we would get the peak from the acetylsalicylic acid and these 2 or 3 peaks from magnesium stearate. And we see here that we cannot use both of these materials together. The GA can also be used for the same application, for the excipient compatibility. And here again, we have in blue the acetylsalicylic acid, as we have seen before. The stearic acid here, it's not magnesium stearate anymore. And here, the superposition, the calculated curve, how it should be. So it's a composition of both curves. But what we do have here in purple is something totally different. So acetylsalicylic acid and stearic acid also interact in a bad way. So they are not compatible, and we have to avoid the use of both materials together. This is also a classic example of incompatibility. But let's use this curve here, the TGA curve of the acetylsalicylic acid. If you remember, from the beginning of the presentation that I showed here, and I asked, was this material or is this material stable until the end of the melting process, given that we do have some deviation from the shift from the baseline. And here we can zoom this section here of this acetylsalicylic acid curve, and we see an inflection here. That means that there is some mass loss. The beginning of the degradation happens at about 140 degrees C, and with a small, really tiny mass change of 1%. But something happened, and the assay was sensitive enough to show that, but we are talking about 1%. So we have to be extremely careful when we analyze this and when we make these assumptions and we calculate things from when we interpretate these curves. Okay. To summarize, we can see from this presentation that the DSC or the thermal analysis really interesting, amazing tool in the pre-formulation to determine the physicochemical properties during the pre-formulation. And just to summarize, a few important points here is that we have to, the pre-formulation is the step or the stage where the physicochemical properties of a drug candidates are determined. And it has to, is essential and has to take place before the formulation process, because then we will save time, resources, money, so it makes the process more efficient. The data generated during the pre-formulation will support a go, no-go decision. In pre-formulation, differently from all other processes in pharmaceutical formulation and production, approximate values are acceptable. And the assays must be validated, but not so rigorously validated as for the formulation and for the product. Here we will have in some case, just an estimation. It's just to say it can go further or not, or at which point that drug candidate is then is not do not have the minimum characteristics to go for it. So it's approved or not approved. Only few techniques are essential for the preformulation: UV spectrometry, HPLC, TGA or DVS, and DSC, and the X-ray powder diffraction. Using thermal analysis methods, we can get information about melting point, enthalpy of fusion, solubility, actually the ideal solubility, which is an estimation of solubility, the purity of the materials, hygroscopicity, polymorphism, and we can do the screening of salts and polymorphs. And finally, I have to say that the NEDGE devices allow for more than just the basics in thermal analysis. The analysis of the evolved gas, the released gases during the analytical procedures can give new insights into the behavior of the analyzed substances, giving such important and valuable information for the decisions that we are going to take. And the coupling of the DSC or the TG or STA with the simultaneous thermal analysis with the infrared mass spectrometer or a gas chromatograph mass spectrometer is always possible. And it's also possible that we have not only one, but two of these gas analyzers coupled to the device. Here you see, here in the middle, you see that a TG coupled with this small but totally effective infrared spectrometer here on the top. Okay, all these materials or all these examples you can find in our website. We have many application notes. These 5 I have used here. And besides these application notes, you can find more information in the thermal analysis in the pharmaceutical field, which is a book with more than 35 examples of application in pharma, but not only the examples, the explanation and the discussion about the results. And besides that, you can also get information about the basics of the theoretical background of each of these techniques, not only the thermal analysis, but the SC and TG, but also thermomechanical analysis and dynamic mechanical analysis. So you can have a look on it in our website as well. With that, I'd like to thank you again. And if you have, so it's already 5 p.m. And yeah, I would like to leave here my email. If you want, you can send me your questions. I will be glad to answer that and to give the information that you need, not only about thermal analysis, but also about rheology. Someone has asked me if you can have a copy of this presentation via mail. You can ask me, so I can send it for you, but then you can ask me again using my email. It'd be a pleasure to send it to you. And you also can later on demand check this webinar. And the other questions I'm going to answer with pleasure by email. I would like to thank you again for being here with me during this presentation, and I hope that we can meet or we can talk once more in the future. Thank you very much and see you on the next opportunity.